can able to do equalization in an upcoming 5G 6G communication that we are going to discuss. So all of us know that in digital communication, this is an overall block diagram. Here the data source send the particular signal which is get encoded and modulated with various type of modulation scheme, and this physical channel may be a wireless channel or a wired channel like a fiber optic cable it may be, or it may be completely a wireless channel in which there are some noise component gets added, and we are considering mostly additive white Gaussian noise, and then the signal get received at the receiver side. On the receiver side, there is a demodulation process based upon whatever kind of modulation we are incorporating over here. The demodulation will be taken place, and there is a equalizer we are introducing here, and I will be focusing on this particular equalizer design for various communication systems, and considering various type of traditional and intelligent techniques, how we can effectively able to design good equalizers. Then that will be followed by this decision device is a part of the equalizer thing, and followed by the decoder of the channel that gives us the signal which we will be receiving at the output. So over here the objective is to design an effective equalizer, and equalizer normally responsible for reducing the following effects. First one is inter-symbol interference. All of you know the ISI. Once the symbols get transmitted over the channel, the symbols normally get overlap with each other if there is not enough bandwidth is there. Then we need to do some mechanism to reduce this inter-symbol interference. Along with the inter-symbol interference, there are other interferences also happens in wireless channels, that is the adjacent channel interference and the co-channel interference in a cellular communication. Obviously, the cell size will vary once we go from 4G, 5G to 6G communication. But in all these cases, the cell size becomes smaller and smaller. Therefore, the co-channels and adjacent channel interference also becomes predominated. And the effect of noise is also another very important factor. So considering this particular things, we have to design this channel equalizer, and the channel equalizer will always have a characteristics of inverse modeling. That is, the transfer function of the equalizer should always be inverse to that of the transfer function of the channel, so that we can able to effectively design it in such a way that whatever we are transmitting, the same thing will be received at the receiver end without any disturbance. That is what the aim is. So all of us know about the inter-symbol interference, that when we are transmitting a sequence like 1 1 0 1, if there is not enough bandwidth, then what will happen, that this 1 gets spread up at the received sequence. This is the thing of received sequence. Instead of a sharp rise like this over here, instead of a sharp rise, it is a slow rise over here. And instead of a sharp fall over here, there is a slow fall over here. So when there is a slow fall and there is a slow rise, Here, if this particular region is more than 50% of whatever thing has been transmitted, then instead of considering this one as a 0, we can consider it as a 1. So there is a change in symbol from 0 to 1, and the symbols got overlapped. So that is what is intersymbol interference, and this happens because of multipath propagation in our wireless communication. That is the wireless signals that received at the receiver from various other paths with reflection refraction. And there is band limited channels like the FM radios, in which there is very much limited bandwidth. And the effective way when to transmit and when to receive is normally we decide it considering the eye diagram, as all of you know. And when the eye is open, if you transmit at that particular instant of time, then it is most suitable for our communication, in which the ISI will be very low. And instead, in case of the wireless channels, all of us know that this is one particular cluster of cell, and in this particular cluster there are different frequencies get used, that is different frequency band. Each of these particular color is representing one frequency band, and between the different frequency bands there is a gap, and that is termed as the guard band. Considering the guard band, we can use different frequency range in one particular cluster, and this cluster can be repeated after certain distance, and maintaining between two different cells a certain distance, you can effectively able to really reuse the things. So over here, this the frequency used in different cells, if there is not enough guard band between them, then they will overlap with each other, and that is what is termed as adjacent channel interference. And same frequency is normally used at the center of differently located cells. Like here, if I am using F1, again here I will use the same F1, and here again I will use the same frequency. And if there is not enough distance between these cells, that is, these cells are very close to each other in 5G and 6G communication, then there will be much more overlap between these cells. That is, the frequency will be same frequency reuse will be troublesome. The co-channel interference will enhance. So to reduce these effects in a digital communication channel, we have to effectively model this equalizer part, or we have to effectively design this particular equalizer part, so that these things, whatever is happening in the channel and the noise component, they get compensated effectively. So the equalizer design is a challenging task. It will have two important components. One is the structure of the equalizer, what kind of structure here we are incorporating, and the second part is what kind of algorithm we are using to train this particular structure. The structure can be a traditional filter like finite impulse response filter, FIR filter, or an infinite impulse response IIR filter, or a ARMA type of model, autoregressive moving average type model, or it can be a neural network for nonlinear analysis. It can be a deep learning network as well, or it can become a transformer also, based upon the complexity of what kind of digital channel you are using, or it can be a very complicated neural network model you can also employ over here. Similarly, as the structures of the channel equalizers will become different, and that varies over the time depends upon the channel, so according to the structure you can also use different adaptive algorithms for that, like the least mean square based algorithm, recursive least square algorithm, to back propagation, to deep learning based yellow algorithm you can use. Also you can use the evolutionary computing based algorithms, nature inspired algorithms, okay, swarm intelligence based algorithm. Many such type of algorithms you can able to employ in this adaptive algorithm to effectively train the equalizer, so that the whatever at the output you are going to obtain, that will reduce this error in such a way that whatever you are transmitting, the same thing will be received at the receiver without uh, much disturbance. So this is a simple FIR filter based equalizer with traditional least mean square algorithm is shown, a very simple form of. Here the channel is taken as a communication channel, and a BPSK based modulation has been incorporated, and the input is taken as pseudo random binary input, like +1 and -1 has been taken as input xk over here, and there are three tabs over here, A0, A1 and A2, and this is representing the channel transfer function. That is, you can able to say that over here the output is A0 into xk, then A1 into xk minus 1, and A2 into xk minus 2. All these three things addition will give us our channel transfer function. Then that's get added with the noise component, AWGN component, and at the receiver side here is the equalizer part. So in the equalizer part you can observe that as it is a simple FIR based equalizer, it has large number of taps. That is, over here the transmission side there are three tabs over here, or two delays or three tabs you can observe. Then over here at least twice of it, at least two times or greater than number of tabs we are considering, like H0 to H7, like 8 tabs have been considered over here. Large number of tabs are normally employed over here, because when you are taking a system like this, then what will be the transfer function of this? A0 plus A1 Z minus 1 plus A2 Z minus 2. So this is a FIR system, and when you take a system design of equalizer, it has to build a inverse model 1 by Hz. So when you will design a 1 by Hz, that becomes a IIR filter. And IIR filter normally we do not prefer, because the IIR characteristics is unstable or unstable you can say. So unstable characteristics we do not want. So what we can able to do is, instead of designing a unstable filter, design a suitable approximation of that IIR filter in terms of a FIR filter. So a long-term FIR model has been incorporated over here, and as it is a very simple model, just delay and multiply and summation, so you do not require a heavy learning algorithm, but instead a traditional simple least mean square algorithm can able to train this particular model. So for training purpose, a least mean square algorithm has been taken. Here the target signal is taken as delayed version of the input signal. So the xk as input, whatever we have taken, the binary input, that's delayed version over here. The delayed version is available as dk as the signal over here. So from dk, this model output yk is subtracted, and that gives us this error signal ek. So our objective is to employ this algorithm so that it can able to fine tune this h0 to h7. So h0 to h7 will be refined in such a way that this ek or error square value will reduce with respect to time. So our objective is this error square value, whatever we are considering, this error square should be minimized with respect to iteration. If we are considering I as iteration, then with respect to this error square value should be minimized. That is what the objective of this particular process. So our cost function over here is to minimize this mean square error. Okay, the error square we are minimizing. N is number of samples. It can be taken as 1000, 5000. Here the number of iteration has been taken as 1000 for one simulation. It is shown. Okay. And the error signal, as I told you, it is the difference between yk minus y cap k. That is here this dk minus this yk. Okay. Or you can see it as y cap k minus yk or dk minus yk, that is producing the error. And the weight update with this least mean square algorithm, that weight update at any k plus 1th iteration, that depends upon its previous iteration, plus 2 mu is a constant, and xk, this is your input signal, and this is your error signal. So the weight of this particular filter will get updated with this particular parameter. X1k is our input and ek is our error. So with the progress of time, you know that this mu, the learning rate, is taken between 0 to 1. And over here you observe that when we are training the model with NSR is equal to minus 20 dB and NSR is equal to minus 30 dB, this is the result. So at minus 20 dB, the signal, you can observe from 0 it has started, at minus 20 dB it is achieving the saturation, and for the next simulation it is from 0 it has been started at in and around minus 30 dB it is achieving the saturation. So this is how you can build an effective equalizer for a simple communication channel. But the problem arises because our communication channel is not as simple as that of the FIR filter, but at times it gets affected with various nonlinearities. If you are dealing with an optical fiber, there are various type of nonlinearity component also arise in them, and thereby the channel over here, along with the channel, there is a nonlinear component has been modeled over here, and whenever this nonlinear component arises, the thing become more complicated. So here this, when there is introduction of this nonlinearity, then this equalizer portion, this cannot become become a linear equalizer anymore. So in this equalizer we have to incorporate nonlinearity. Okay, and for effective nonlinear things modeling, neural network is one of the best choice for the nonlinear modeling. So over here you can observe that the output of the system over here, xk, that has been defined over here, xk, as this nonlinear function plus the convolution of the hi, the channel, with the input. So here it is hi uki. This is the convolution of the channel transfer function with the input, followed by this nonlinearity and addition of the noise. So that is what the overall thing that is received. Xk is the signal received at the uh, equalizer, that is at the receiver end. We are receiving this particular signal. So from this signal, our objective is to uh, do such calculation with the equalizer and the adaptive algorithm, so that we can able to minimize this error and we can obtain effective binary signal output at the receiver. So over here, for the nonlinear thing compensation, we can model it as an effective optimization problem. Okay. And whenever we are saying it as a nonlinear multimodal problem, so the complicacy becomes more. And all of you know about multimodal optimization problems. They do have more than one optima. Okay, these are global optima. This is your global maxima, and this is your local maximas. So in multimodal case, simple algorithms like least mean square algorithms, as I discussed previous, this LMS based algorithms, they do not work effectively because they are based on derivative based optimization, and these derivative based optimization get stuck at the local optima. That means wherever the slope changes, they declare that one as a maxima or minima, and thereby they get stuck at those points. Whereas for complex multimodal cases, the results lie somewhere else. So our objective is to determine such solution which gives us effective result in such scenario. So nature inspired optimization algorithms are preferred for training such type of complex networks. And when we say about the nature inspired optimization algorithm, they are, in order to determine the global solution at these points, you have to employ a number of elements instead of one particular thing searching from begin to end. So over here, there are multiple elements have been incorporated. Some of the things they say these are particles, some of them say these are wolves, some of them says they are ants. There are different type of algorithms developed on these, and over the years scientists have reported that all these algorithms are suitable and they gives effective results for solving complex problems. And the most parent algorithm whatever is developed in this particular way, which has been widely applied, is genetic algorithm. And genetic algorithm has been effectively applied for equalization uh, over last decades, you can able to say. Here the most important thing is where we are going to employ this genetic algorithm for the thing. The genetic is applied over here in this algorithm case. The algorithm will be used to train the weights of this particular network. So this particular network is a FIR filter network. So for this particular thing here, in order to calculate the values H0 to H7, you can employ the genetic algorithm. This is a simple FIR based filter. Okay. So for this you do not require a genetic algorithm. LMS algorithm is good enough. But when you do it for a complex neural network structure, like I can able to say you a neural network like this. So over here you look that this delay followed by a complex neural architecture. So this neural architecture weights, these get trained with the genetic algorithm over here. Why? Because the regular LMS algorithm cannot able to effectively uh, do the calculation of the weights in case of nonlinearity. And here this nonlinear function is present at the channel that makes the thing more complicated. So for compensating this particular nonlinearity, you need a neural network structure like this, and that one's weights to be trained by this type of genetic algorithm and other nature inspired algorithms network. So for those who are new to this genetic algorithm, I can able to say that the weights of these neural networks that are one parameter, okay, or FR filter weights, they are one parameter, and our objective is to calculate these parameters in such a way that the error square has to be minimized. Okay, so for effective calculation of these parameters, you need to determine their values. Okay, so to determine their values, each of the weight is represented as a candidate solution. So for solving this particular problem using genetic algorithm, each of the weight component like W0, W1, W2, each one will be represented, each one set solution will be represented with a genetic uh, pheromone, which is genetic thing, is known as a chromosome. Okay, so here X represents one particular solution. Okay, one line represents one solution, and like that there are multiple lines, each of them representing one solution. So over here there are 5 solutions you can able to observe, and each of the line represents one solution for the weights of the neural network or weights of the filter. Okay, so over here after this type of binary initialization, you can able to perform the crossover and mutation mechanism with which you can generate new solutions. Okay, so over here there is one point crossover, that is any random point you can able to take, and then a swap over of the things, that is they from these two chromosomes we can generate two new solutions. Okay, so these two new solutions are generated like this: 10110, then followed by below 10111, and 01011, then up, then 10010. So like that with this swapping as shown in this particular diagram, from top to bottom and from bottom to top. Okay, so this way with exchanging the portion of the parents value, we can obtain new solution, and these new solutions are termed as children's. Okay, so why we do this particular process? So that we can get new solution, and these new solution or new weight values may be better than whatever was the original weight values. Okay, so our objective is to determine effective weight of these equalizers, which can give us very good results. Okay, so another step after the crossover is mutation. In this mutation, what we do, some of the random locations we do change. Over here you can observe, here these portions 1 and 0s, they have changed. 1 is changed to 0, 0 is changed to 1 with certain probability. Oh, that means certain lower portion, that is 1 or 2% of the chromosome in the entire thing, will be changed. And when these values you change from 1 to 0 or 0 to 1, again new values get generated and new weight factors you will get. And these new weight factors will contribute towards the refinement of the weight of the neural network or the adaptive filter. Okay, so over here you can observe a pink color one is getting converted into a green color one. Okay, so with this, whatever was the original weights we have taken, we are considering them as original parents, and with these crossovers new children have been generated, and with mutated new children have again further generated. So out of all these combinations, which one is better? So we have to sort the best chromosomes or best weights as per their fitness evaluation, that is whichever weights are giving us best results for the neural network, we are going to keep them, and rest things we will be discarding them. So best fit population will be acting as parents for the next generation, and thereby for a couple of generations we will be training this particular network. So this is the flow of the genetic algorithm for solving this particular problem. I told you that crossover, mutation, and offspring generation are the important part of this particular problem. So for this equalizer, I told you that we have to take some of the input signals, and these input signals will pass through the filter or the neural network, and then the error will be getting generated. So suppose we are saying that there are 1000 inputs samples we are considering as inputs. Then for these 1000 input samples, all are with 1010 bits up to 60 chromosome with we are considering. Okay. Then for each one particular line is representing one set of weights of the filter or neural network. Then for 1000 samples, there will be 1000 desired values will be there. And from those desired values, we will get the model output as YK. So this difference will create error. So for 1000 samples, there will be 1000 errors will be there. So when 1000 errors will be there, then this one's we can calculate mean square error. How we can calculate? E1 square plus E2 square like that up to E1000 square. E1000 square divided by 1000. So that is giving us a mean square error. So this is equal to this mean square error, MSE. So we calculate one mean square error over here. Then like that, there are 60 chromosomes are there. So for 60 chromosomes, there will be 60 mean square error we will obtain. So among these 60, which is lowest? So that one we need to compute, and whoever mean square error is lowest, that will give us an effective result. So this is what the mean square error minimization is considered as a effective solution over here to be obtained with genetic algorithm. So as I told you, the objective is to minimize this mean square error. Okay. And we are considering the population initialization, that followed by selection, crossover, mutation, and fitness evaluation as the procedure to move forward, so that we can obtain minimum MMSE, that is which gives us the effective result for obtaining the solution. So one of the example over here is taken like the input signal action X is taken as pseudo-random binary input. Noise we can able to take white or uniformly distributed with 30 dB or 10 dB. Then number of input samples can be taken, like the input signal xk is taken as 1000, and the number of channel parameters to be optimized is 8. So here there are 8 number of weights of the FIR filter or neural network we are trying to train. So this is the thing system simulation is shown. Over here the channel is taken as a FIR filter with 0.26, 0.93 and 0.26, three parameters. Like this H0 is taken as 0.26, this is here, and H1 is like 0.93, and this H2 is like 0.26. So over here, three parameters have been taken, and they are which followed by this nonlinearity. This nonlinearity can take the values like tan hyperbolic thing, or it can be a squared cube like thing, like over here square is there, over here cube is there, or it can be a combination of both square cube as well as the trigonometric nonlinearity. Depends upon what kind of complex nonlinearity the system poses over here. Thereby followed by this is your noise. Okay, noise. So when we add noise, then the overall system becomes nonlinear, and over here the GA is employed over here, and from the desired signal is obtained with this delay, incorporating this delay over here. So from this decay to this model output yk, the error is produced, which is to be minimized over here by training these weights from W0 to W1 to W7. These weights we are going to train such a the error gets minimized. So considering this, you can observe that this is the result when we are considering very high noise, that is 5 dB SNR. You can observe these BER plots, bit error rate plots. So you can observe that the black one is this genetic and immune system based algorithms. They are giving much better results in these three nonlinearity scenario. Nonlinearity 1, 2 and 3. Okay, in all the three cases, this black and dotted lines are giving better result for these three nonlinearities. F1 is tan hyperbolic, second is square cube, and third one is square cube plus cosine nonlinearity. So in all three nonlinearity case, the genetic algorithm performance is better compared to this LMS, which is derivative based algorithm. It is not at all performing good. You can observe that the results are not at all good. Whereas the GA and the AIS based algorithms are giving us superior, better results. And this is another simulation with 10 dB SNR. Okay, so 5 dB 10 dB SNRs are very high noise conditions. In these scenarios the results are superior. So as I told you that the FIR filter, along with that the neural network is a very important role, and we have published one article on solving these problems with wavelet neural network trained by another genetic type algorithm that is known as symbiotic organism search algorithm, and this is published in Applied Soft Computing Elsevier. So over here I will explain this one. Here I am taking just 2-3 minutes break, and then I will be resuming this particular session. Dr. Geeta, here I am taking 2-3 minutes break, and I will be starting it again in 2-3 minutes. Is it fine? So, dear participants, if you have any query till now, whatever I have taught, you can write in the chat if you have any query. So over here, I hope I am audible and things are running fine. Hello.
Yes, sir. Audible, sir.
Okay. So over here, moving further for the equalization. Here, I told you earlier that the nonlinear function makes the thing complicated, and in order to solve this one, here we have taken a wavelet neural network into consideration. Wavelet neural network means over here we have the neural network, the neurons, at these neurons there is wavelet function have been taken into account, and the wavelet function you can able to observe, this is the mother wavelet function that is taken into account, and that one is expressed in this particular format. So our output of this model, wavelet neural network model, is comprised of these weights multiplied with the wavelet function of the x, and this summation is being subtracted from the desired output, and that gives us the error, and the error is minimized with a recently developed nature inspired algorithm, that is symbiotic organism search SOS algorithm, with which the error has been minimized and the equalizer is giving us the perfect output. So this, like the genetic algorithm, this symbiotic organism search algorithm is very popular, which is also inspired from a natural system, that is an ecosystem. You can say the entire environment is an ecosystem, and which is divided into three particular mechanisms. One is mutualism, another one is commensalism, and another one is parasitism. So in this entire ecosystem, these three things together work so that there is a balance among the ecosystem. And the first paper on this particular algorithm is reported in Computer and Structures Elsevier in 2014. After that, this algorithm became very popular. So in this algorithm, this solving this equalization problem, the organism is referred to the weights of this equalizer, and over here suppose we are considering there are d number of weights associated with the equalizer. So one particular organism solution O1 is represented by 1 to D. That means D number of weights are there, we have to calculate. And here each organism is representing a solution for the weight. And there are P number of such organisms have been taken to determine the solution over here. So after this, for fitness evaluation, same as that of genetic algorithm, the each of them, the mean square error is taken as weight for weight optimization. Then these three process will be followed. Let's discuss about this phase. The mutualism, in this mutualism phase, two different entities will interact with each other, and they one of them means uh, gets benefited as well as the other one as well. So over here, this is also termed as the phase of benefits of for all the participating organism, such as example between cow and grass. So when cow grazes the grass, cow fills its stomach, as well as grass also obtain a growth. So it is a win-win situation for both cow and the grass. So both the organisms which are participating in this particular process both get benefited, and thereby the participating things update equations have been defined in such a way that mutualism between two different organisms like cow and grass, one is y and another one is j, oj, and I is not equal to j. So both for both of them, the benefit vectors have been defined like this. Okay, so I position is get updated to I new, and jth position get updated to j new with this mutual vector that is assigning into a multiplying benefit factor. And from the best component in the whichever is the best one in the environment, from there a subtraction is giving us these weight updates. So these are the weight updates that will be available after one phase of mutualism, and the mutual vector is defined like this. It is the average of these combination y plus oj by 2. So this benefit vector randomly takes values as 1 or 2, and with these two update equations, we will obtain the output of mutualism as ith organism update, jth organism update. So it will be 2 times that of the population. So whatever is the population size, suppose 50 populations you have taken, then for both the things benefit, you will obtain 100 populations over in this phase. Then the second phase I told you is commensalism phase. In this commensalism phase, the interaction between two organisms, only one will get benefit, while the other one is neither get benefit or not suffer from this particular relationship. For example, the shark is a very big fish inside the ocean, and there are small ramora fish. You can observe this is a picture of a shark, and these are small ramora fish behind the shark. So shark as a bigger fish, it hunts for it, and some of the portion which is left over, that is taken by this ramora fish. So these ramara fish, they align themselves behind the shark. So shark does not, their movement does not affect the movement of the shark. Okay, a shark is not neither get benefited or not get harmed by this movement of ramara fish. But these ramara fish, they fill their stomach with the leftover food whatever shark is leaving. So this ramora fish, this shark is helping the ramora fish to survive for long in the environment. So like this, there are many such examples you will find in a regular environment, that some of the creatures, they are dependent upon the leftover food of other creature. So in such a kind of scenario, the update equation is like this, that any ith particles update will be dependent upon its previous location, a random number plus the best organism minus the other organism which is giving us the benefit. With this particular update equation, so this O best minus OJ, this particular component is the benefit provided by the shark fish to the organism. So with this particular way, the weight of the filter or the neural network will get updated by considering this update equation, and OI new is the new weight update that you are going to obtain after applying this particular commensalism phase. And the third phase in this particular algorithm is known as a parasitism phase. Okay, so in this particular way of interaction in the environment, the weaker organism gets eliminated from the ecosystem. So two things are interacting, so one will get benefit and other one will get eliminated out of the interaction. So over here, that means it is a survival of the fittest. One particle will survive and other one will be eliminated. So this one has been mathematically modeled like this: the parasitism between two organisms Y and OJ, and I is not equal to J, that is, their interaction creates like a interaction between a mosquito and human being. So if the mosquito, what it does, it creates a parasitic vector when it inserts the parasites in the human body. If the human body is strong enough, then this parasite vector will be eliminated. Otherwise, if the human being body is weak, then it will be affected by dengue, malaria, and many of these parasitic thing, and the human being may die also. So one thing will be get eliminated out of the ecosystem. So that is what, whose fitness factor is better, that will survive for long. Either OJ will survive, otherwise PV will survive. OJ is the human being and PV is the parasitic vector. So considering this particular algorithm, so first we need to initialize the position, that is the position of the organisms, that is the weights of the neural network. Initially we have to do. Then the fitness of these weights we need to calculate. Then followed by three important parameter update mechanism, that is mutualism, commensalism, and parasitism will be incorporated. Then best fit organism fitness will be evaluated, and that will be followed by the termination criteria, that is the mean square error is up to the desired level or not. So with that, the process will be get repeated until and unless the final position gets settled and the optimal position of the organisms get reported. So here the simulation have shown on two different channels. That is, the first one is the same channel that has been taken 0.26, 0.93 and 0.26, and another channel on 0.34, 3040, 0.9030 and 0.3040. These two channels have been taken, and the simulation has been shown for two different nonlinearities. And with these nonlinearities, you can able to observe that this is the mean square error minimization curve, and this is the bit error plot for this three channels in the channel 1. So obviously this black one is giving us this better effective result in terms of BER up to 10 to the power 5 bits, when it has been 10 to the 5 to 10 to the 6 bits have been taken into account. So the simulation further states that there are many structures have been taken for the channel equalization, like the wavelet neural network I discussed, that has been compared with functional link artificial neural network, another neural network based model, radial basis function neural network, another neural network based model, and the finite impulse response filter based model. So all these four architectures have been trained by several algorithms like the symbiotic organism search algorithm. There is genetic based algorithm, there is particle swarm optimization algorithm, there is least mean square algorithm. All these algorithms with the nonlinearity 1, the training has been carried out and the mean square error obtained has been reported over here. And the testing has been carried out considering the BER value at 20 dB. So the results have been reported over here. You can observe that this symbiotic organism search is giving us effective result in all the architecture values. Okay, considering different architectures, these values have been reported to be better compared to the other algorithms. So then we have applied this particular equalizer on a 16 QAM telephonic channel equalization. Okay. So over here in this telephonic channel equalization, like I told you, there are three tabs in the previous case. Like here, there are three tabs: 0.26, 0.9298, and 0.2602. Here in this case, there are 21 tabs are there. So the tab number is 21, and each of the tab has a real component as well as imaginary component. So it is a complex channel. So it is a complex channel. So for complex channel equalization, this experiment has been carried out with 21 number of tabs, you can observe. So considering this is the symbols before equalization, you can observe that as it is a 16 QAM, so ideal location should be 16 different points. So these 16 different points before equalization, because of the noise and all, these have been spreaded into such type of bulky clusters. Ideally, this should be a point, a narrow point like this. So because of the spread of the symbols and intersymbol interference, the 16 QAM symbols have been very spreaded over here. And after equalization, you observe that instead of such bulky spreading, it has been squeezed to a very narrow value on its right side. You can observe that this is the effect of the equalization. From this particular huge amount of spread to it has been narrowed to a very small extent. So you can observe that here also it is a very small uh, uh, point. Okay, so this from this constellation diagram you can clearly observe that from the large spread to the very small value it has been squeezed. So squeezed means these all symbols are at one location, almost approximately to a very one location. So after equalization the results are much better. So on the telephonic channel also, for different type of structure, we have observed that for wavelet neural network, functional neural network, radial basis function neural network, and a fire filter, the results are better in case of the SOS algorithm. Okay, so the parametric estimation is much better. Then we have moved for another experiment on a channel equalization for the IAR communication channel. IIR channel has a special importance because they do have always a feedback component and they are unstable in characteristics. So you can observe this IIR channel has a feed forward component like this over here. From the input, this is feed forward type. Always till now we have discussed only the feed forward component for the analysis, that is this, the input delayed for certain time, and that gives us the output. But along with this, in this IIR filter, there is a feedback path. So you observe that this particular one, this feedback component plays a very important role, and thereby from this IIR filter, you observe that this feedback component, this feedback path which is subtracted from this, that's give us the IIR component, infinite impulse response component, and from this plus and minus, this gives us the result output of the channel equalizer, which is then followed by this noise. This noise component is here. So feed forward path, feedback path, followed by noise. That makes the system more complicated. So in such scenario, still if you are thinking that addition of nonlinearity, then that makes the system really more complicated things. So for under such scenario, for equalization, you can observe that this has equalizer as a IIR component. Again, here also this feed forward path is there and feedback path is there. Both part has been considered to in the modeling, and whatever is the input that is given as the desired signal over here to minimize this error. So this equalizer model weights have been trained by MFO algorithm, another nature-inspired algorithm, that is moth flame optimizer based algorithm. So any of the nature-inspired optimization algorithm you can use for such FIR IIR structure equalization, as well as for the neural networks based channels equalizer design as well. You can able to employ such type of thing. So over here a practical aspect have been given over here. You can observe that as I told you, it has both pole zero components over here, the upper part as well as the lower part. You can view that this, along with this key component, this hmm, IIR systems equation has been defined with this, and the nonlinearity taken over here is taken as a hyperbolic tangent function. And comparative BER analysis, beta rate analysis with respect to the signal to noise ratio, that has been plotted over here for various algorithms. So you can observe that the LMS algorithm, least mean square algorithm, which is completely flat, is not giving us very effective result. The algorithm is completely failing, you can able to say. Whereas the other algorithms like the genetic algorithm, MFO algorithm, they are giving us better result over here. We are getting in such complex IIR system also, we are getting a good BER performance in this scenario. So there are these are the important papers we have produced in last several years, and you can apply these go through these particular papers, and you can apply these many more algorithms also in designing such type of system And another very important aspect that in these days for the neural network and the complex networks weight learning algorithm, you can also use can able to use multi-objective optimization scenario. So multi-objective optimization, you can simultaneously train the weights of the neural network as well as you can able to target the structure optimization of the neural network as well. So two aspects. One is the efficiency of the neural network should be very high, as well as the structure of the neural network should be also very competitive, because you cannot able to spend more and more time in training the neural network a very complex architecture and then obtaining the solution. So it is advisable that you make a compromise between the time complexity for, for the training as well as the efficiency of the neural network. For the particular system channel equalization, how much efficiency is required or how much accurate the system should be, and how much complex the system should be. You make a compromise between the complexity and the accuracy. So these two things are actually contradictory problems. In multi-objective optimization, we normally do a compromise between different type of objective functions. So contradictory objectives we normally try to solve and try to determine a Pareto optimal solution between two different contradictory objectives. So when you say about the neural network efficiency or accuracy, that is one parameter. And when you say about the training of uh, about the complexity of the neural network, that means the structural aspect of the neural network, its optimization is another objective. So considering these two objectives, also you can effectively able to design a future neural network based equalizers, which will be very prominent for the upcoming communication systems, because AI and ML algorithms in upcoming 5G 6G communication will become very important. So various latest type of neural network like convolutional neural network to transformer to you can say large language model based networks. So all these things you can able to employ in this upcoming future for solving many communication related problem. And uh, as the structures will become complex, the corresponding algorithms will also become complex. So under such scenarios, it is very important that you do the necessary trainings in an effective manner and try to analyze the results and report them effectively for the next generation communication systems. So, participants, now we will check that if you have any queries till now, whatever I have taught you, you can write in the chat box. If you have any queries, let's first take your queries. Uh, uh, One question is uh, here by Binita N. What do you mean by complex channel? How it can be described? Like one example, I have told you that 16 QAM based telephonic channel. Okay, there are 21 number of tabs, and it's all tabs functions are complex. You can say they are complex numbers. Okay, so there is real and imaginary part. So the channel transfer function is in complex, and that is followed by nonlinearity as well. So when you are designing the thing in the complex domain, as well as complex domain means complex numbers, as well as there is nonlinearity, then to equalize such type of system transfer function is very difficult, and you have to really use the mm, neural network based complex models to solve such kind of problems. And deep learning based architecture also you can able to employ for such a type of for solving such type of channel equalization problems. And normally you can say like telephonic channels, recently we are also employing this equalization of the optical channels also. So optical communication channels, they do also have the very complex nonlinearity and phase destruction, and other complex scenarios happens in a optical fiber channel. So at the receiver end you can able to employ such type of AI neural network based technique, so that you can compensate whatever problems is happening to the data in the fiber while doing the transmission, so that you can recover those things at the receiver. Binita, yeah. Another question, that in case of multi-objective parameters optimization, which optimization technique will provide best result? So there are many multi-objective optimization algorithms that have been reported by several researchers, but one of the most prominent one is by Professor Kalyan Dev, uh, who has introduced the NSGA2 algorithm, non-dominated sorted genetic algorithm 2. So let me write in the chat box so that you will get a idea. Non-dominated sorted genetic algorithm. It has version 2 that came up in actually 2002, and its NSGA 3, its paper came out in 2013. Okay, so these are by Professor Kalyan Maidev of Michigan State University. So you can explore this particular thing. Actually, Professor Kalyan was earlier there at IIT Kanpur. Okay, now he has from last one decade, I can say, he has moved to, or more, he has moved to Michigan State University, USA, and his papers on this NSGA2 and NSGA3 algorithms, these you can able to explore. So if you use such type of things, then they will obviously give you better result, compromised result for these channel equalization cases. Uh, And along with that, also you can able to use multi-objective particle swarm optimization algorithm as well. Multi-objective particle swarm optimization algorithm was reported by Professor Carlo J. Coelho, who is a very famous Mexican researcher. C.A. Coelho, Professor. I am writing here in the chat.